Hello and welcome to this What's New video, presenting the latest developments in the NVH domain for ANSA and Meta, version 24.1.0. The FRF assembly tool introduces an innovative feature called disassembly. With this functionality, it becomes feasible to compute the unknown transfer functions of a subsystem by leveraging the known transfer functions of both the full assembly and other components. Access the FRF assembly tool from the menu Calculate. Switch the mode from assembly to disassembly and notice the change in the interface. Components list remains as an assembly mode while two new lists are appeared containing the degrees of freedom from the excitations and responses accordingly. As an example, we use two components where the one of them hasn't transfer functions and need to be calculated. Let's start reading the components to understand the method setup. Initially, the full assembly UNV file is loaded and defined as the full assembly by selecting the respective radio button. Afterwards, the first component is loaded, providing its corresponding UNV file. Once the file is loaded, the FRF assembly matches the common transfer functions between them and shows them in the lists below. Next, the second component with the unknown transfer functions is created without providing its UNV file. Please notice that is marked as undefined. Following actions involve the creation of connections between the two components. In this case, an existing connection file is used to facilitate the process. After the calculation is completed, a new 2D window is created displaying the transfer functions of the subframe. Changing to logarithmic axis make the responses visible. The calculation verification will be fulfilled by comparing the calculated transfer functions against the known transfer functions from the UNV file. Overlaying the corresponding curves shows a perfect match. An additional enhancement regarding the UNV component is the capability to handle missing transfer functions as zero values. This is a useful option when transfer functions have been generated by physical testing, as it is quite possible that some transfer functions might be missing. It should be noted that if the reciprocal transfer functions exist, then the direct transfer function will be considered known. Let's consider an example using the FRF assembly tool, where two UNV components are analyzed. Navigate to the main menu, and under the Calculate, scroll to the FRF assembly tool. The analysis is fully defined, but full check reveals that the powertrain component has some missing transfer functions. These will now be assumed as zero by selecting the respective option. Checking again confirms that the missing transfer functions have been identified as zero, allowing the analysis to be started. All NVH tools now support the HDF5 file format, which is exported using the keyword HDF5out. Specifically, in the modal response tool, enhancements have been made. A new option in the settings allows users to control the consideration of phase in equivalent radiated power calculations. A new nodal result feature has been developed, enabling the calculation of grid point forces for both 2D and 3D outputs. Let's see an example regarding the grid point forces. A model is considered consisting of two plates, connected by a strip structure and constrained at their perimeter. Navigate to the main menu, and under the Calculate, scroll to the Modal Response tool. The modes of the model has been loaded. Switch to the Frequency Response tab. A sinusoidal force is exciting one of the plates in z direction. Below, the frequency range has been defined. Respectively, two types of responses have been defined. The first response outputs at all grids the forces in the 3D window, and the second response outputs in a 2D window the force of a specific node. Let's start the calculation and examine the results. The 2D results plots the nodal force over the frequency and the forces of the adjacent elements. In the 3D window, the grid point forces are plotted according to respective direction. Regarding the enhancements to the modal response tool, it is now possible to calculate structural intensity for transient analysis. In the following example, a sinusoidal force excitation is applied for 50 milliseconds. The corresponding response is obtained by selecting the variables of mechanical and sound intensity. As an example, we have a model consisting of two plates connected by two bushes and constrained at their perimeter. In the modal response tool, a sinusoidal force is applied at a single point as the excitation. Below, the simulation time has been defined, requesting an output of 0.2 seconds. Respectively, two types of 3D responses have been defined. The first response plots the nodal displacement for all nodes in the model. The second response outputs the mechanical intensity for all elements in the model. Let's start the calculation and examine the results. A sequence of states has been generated for each time step. By animating through these calculated states, we can visualize the transient response of the model. The mechanical intensity results are displayed based on a color scale. Next enhancements are within the modal parameter estimation tool, such as option to automatically stop the polyreference LSCF algorithm at an order lower than the maximum. Capability to output the residues FRF to residual vectors. Option to generate functional mockup unit. Export of modal damping of the estimated modes. For the purpose of demonstration, some measured FRF functions have been loaded in Meta. Let's open the tool found under the Calculate menu. A new analysis needs to be created that will host the selected method. The polyreference LSCF method is selected. In the next step of the wizard, select All to collect all the measured FRFs loaded in the 2D window. In the analysis settings is the first new feature, called Auto Stop. By selecting this option, the pole estimation algorithm will stop automatically when the optimum number of stable modes has been reached. As an example, we set a high maximum model order for this particular case while have unchecked the option Auto Stop. Select Next to see the accepted poles. We observe their rank has reached the maximum order provided. By repeating the process having checked the Auto Stop option, the algorithm will stop to a smaller rank. Moving to the last step of mode shapes, we observe three new features. The first is the option as compensation modes, which operates along with the drop-down menu of output residues. Upon selection, the generated universal file will contain residual compensation modes instead of residual frequency response functions. This option captures dynamic effects out of the frequency range, enhancing the prediction accuracy when a modal component is created based on these modes. As an example, we create two universal files for each option respectively, and the resulted universal files will be compared within the modal response tool. The first universal is generated without compensation modes, and the second one with compensation modes. Opening the modal response to review the outcome. As can be seen, the options resulted to 2 additional modes at low and high frequency, respectively. The second new feature is the option Export Modal Damping in Tab 1 format. Let's create a file and then use it within Modal Response tool, as an example. Switch to Modal Response and navigate to the tab Tables. Click on red button to select the file. Check the Preview Tables as curves for a quick look on the result. In case the table needs to be applied on the modes, this is feasible by selecting it from the B-Table field. Last but not least is the new option to export a functional mockup unit, which can be used for model exchange and co-simulation of dynamic models. Export process is the same as before. Typing a file name and press Finish. Moving to the 2D plot enhancements, the modal effective result type is now supported. Modal effective mass indicates the mass participation of each mode in each of the 6 rigid body motion directions. As an example, we read a file containing such results as can be seen under the results type. Only the translational degrees of freedom will be selected, and from the Settings tab, the option of 1 curve per plot will be selected. The plot description is defined accordingly. Plotting the modal effective mass fraction and examining their cumulative sum can indicate whether the selected frequency range for normal mode analysis captures the entire model mass. Regarding the NX-Nastran solver, it is now possible to read acoustic power and transmitted acoustic power results. The respective keywords of AC power and TR power has to be provided in the case control command. Such a kind of results can be found under the scalar result as usual. Regarding PERMAs, the modal response tool now supports reading uncoupled structural modes and fluid modes from HDF files. Additionally, the calculation of fluid structure interaction and all participation factors is now available. There are also new features in the 2D plot functionality. Specifically, for frequency response results, complex displacements and modal participation are now available in both .post and .hdf files. Furthermore, modal contribution is also provided for transient analysis. Let's explore an example where a simplified structure of a cabin is coupled with its cavity. A normal mode analysis has been performed for both, and the result files have been loaded into the modal response tool. Navigate to the Calculate menu and select Modal Response to open it. The modal results input files for both the structure and the fluid have been loaded. The list below displays them in frequency order, with the fluid modes at the end written in italic fonts. Switch to the Acoustic Coupling tab, where the coupling between the grids of the structure and the fluid has been calculated and defined. This calculation can be performed using the appropriate tool found under the New button. Next, switch to the Frequency Response tab. For excitations have been defined, all acting in phase vertically at the base of the cabin. A linear frequency range has been set up to 500 Hz. A noise transfer function is requested as the response, with a modal participation analysis on top. Submit the analysis by clicking on Calculate. A new window is generated containing the pressure participation analysis. With the help of Fractions window, the participation options are available, such as the selection of the peaks. A unique feature for root cause analysis enhancing the potential of the PERMA's modal results. In the next step, let's review the 2D available results. Switching to the Curves tab, time history as well FRF result have been loaded. By selecting all of them, all the supported result types can be reviewed at the Results tab. Regarding the enhancements on user toolbars, the equivalent radiated power toolbar can now display the current and estimated memory usage before and after calculations. time performance has been improved by 65%. New capabilities are available under the Settings tab, such as the definition of a frequency-dependent radiation loss factor, the consideration of the phase of normal velocities when summing ERP results by property or set, the option to treat shell elements as solid skin elements, with the latter having only one radiating surface in contrast. Concerning the Directivity Plot toolbar, several new features have been introduced. The toolbar can now retrieve existing results. Field points can be defined through a set of nodes, cut planes, or A/LC points. Changing the analysis type to 3D enables pressure calculation in a 3D field. Additional plot types are available, including polar plot, polar map plot, off-axis plot, and waterfall plot. The option of band averaging is now provided, selecting either the linear or the root mean square averaging. The following example involves an exterior acoustic analysis of a vibrating gearbox. The geometry and the results have already been loaded. Navigate to the User Toolbars menu and scroll to NVH Directivity Plot. For a 2D analysis, the periphery needs to be defined by selecting one of the available options such as node set, cut plane, or ALC points. For simplicity, the last option is used. In the Post-Processing area, under the Settings tab, select the new band averaging capability. Go back to the Results tab and create some plots for all states. For a 3D analysis, a field should be defined instead of the periphery. Create a new set with the help of feature selection. For all selected states, the pressure can now be plotted as normal displacement, visualizing the direction of sound pressure in the 3D field. Moving to the next toolbar, the damping estimation graphical user interface has been restructured. New features have been added to handle the peaks list, including peak identification and removal from the list. Modal damping can now be exported in Nastran format using the tab1 keyword. Let's see an example. For a given acceleration response, the modal damping will be calculated using the toolbar. Navigate to the User Toolbars menu and scroll to NVH Damping Estimation. Once Calculate is pressed, the list will populate with the modal damping values at the respective peaks. The Identify button will locate the peak in the plot, while the Remove button will delete it from the list. ANSA development has focused on integrating additional features for Actron. 4 new features have been added. The boundary condition of the electric potential is now supported. The infinite admittance boundary condition is also supported, which can be useful for modeling radiation above an absorbing surface. ANSA now provides the capability for the multiple creation of domains. The component modal_driver is currently supported, which is particularly useful for loudspeaker analysis. NVH-related developments in Epilisis containing the analysis of acoustic and structural participation factors make use of the AMLS method, enabling faster results generation. The calculation of the transient intensity results is now feasible. The keyword W-modal can now be employed in a transient response analysis to enable the use of material damping. Thank you for watching.